Somewhere above the Earth, a mirror the size of a tennis court is drifting in silence, a million miles from home, staring into the dark with a patience no human eye could ever manage. It does not blink. It does not tire. And for years, it has been listening to the universe in a language made of infrared light, waiting for one particular kind of whisper. On a quiet day, without warning, without a press conference, without the fanfare that usually accompanies a discovery this size, that whisper finally arrived. Buried inside a faint ring of dust circling a young star more than 100 light years from Earth, astronomers found something that should not have been visible at all. A planet, not a shadow of a planet, not a mathematical inference drawn from a flickering star. An actual, physical, glowing point of light, captured directly by the most powerful telescope humanity has ever built. And once the researchers understood what they were looking at, the room reportedly went quiet. For most of the history of exoplanet science, nobody has ever truly seen another planet. Thousands of worlds have been cataloged beyond our solar system, and almost none of them have been observed directly. They were detected because a star dimmed for a few hours as something crossed in front of it, or because a star wobbled ever so slightly under the gravitational tug of an unseen companion. Astronomers built entire careers analyzing these tiny disturbances, extracting planets out of pure mathematics, describing worlds they would never actually witness with their own instruments. It is a bit like trying to describe a person's face by only ever watching their shadow pass behind a curtain. You can guess the shape, you can estimate the size, but you never actually see them standing there. That is what makes this moment different, because for the first time, one of these worlds did not have to be inferred. It had to be looked at directly, and it was there. The star at the center of this story is called TWA7, a young, faint red dwarf sitting more than 100 light years from Earth, still early in its life, still surrounded by the raw material left over from its own formation. Around it spins a vast, faint disk of dust and debris, the leftover scraps of planet formation, arranged in delicate rings like grooves on a record. Astronomers have studied disks like this before. They're common enough around young stars. What is not common is finding something moving inside one of those rings, something dense enough, warm enough, and bright enough in infrared light to stand out against the glow of dust that surrounds it. And yet, when the researchers pointed the telescope's coronagraph at TWA7, blocking out the blinding light of the star itself the way you might cup your hands around a candle to see past its glare, something emerged from inside the second ring of debris. A single point of orange light, sitting in a gap where the researchers had not expected to find anything at all. At first, caution ruled the room. Scientists do not celebrate the moment they see something strange. They interrogate it. Could this be an artifact of the instrument, a flaw in the data, a trick of processing? Could it be a background galaxy, a distant smear of ancient light happening to land in exactly the wrong place at exactly the wrong time? The team calculated the odds of that particular coincidence, and it came out to less than 0.5%. The evidence, gathered piece by piece, pointed overwhelmingly towards something real, something orbiting, something that belonged to that star. They gave it a name, TWA7b. And when they finally worked out what it was, the numbers alone were enough to make seasoned astronomers sit up. This was not a monstrous gas giant several times heavier than Jupiter, the kind of planet that is comparatively easy to spot because it is so large and so hot that it practically glows on its own. This planet was estimated to carry a mass somewhere close to Saturn, and later analysis suggested it could be even lighter than that, potentially only around 100 times the mass of Earth. To put that into perspective, it may be roughly 10 times lighter than anything ever photographed directly beyond our solar system before it. For an instrument to catch something this faint, this small, this impossibly dim, next to the blaze of its parent star, was considered by many in the field to be near the edge of what technology should currently be capable of. Imagine trying to photograph a firefly hovering a few inches from a lighthouse beam, from 100 miles away, through a hurricane of dust. That is roughly the scale of the challenge these astronomers were up against. A star is not just bright. It is blindingly, catastrophically bright compared to anything orbiting it. Planets do not produce their own light the way stars do. What little glow a young planet has comes mostly from residual heat, the leftover warmth of its own formation, slowly radiating away into space. Detecting that faint infrared signature, buried inside the overwhelming glare of a star entangled inside a ring of dust that is itself glowing in the same wavelengths, is one of the most difficult observational problems in all of modern astronomy. And yet, it worked. To appreciate just how narrow that margin for success actually was, consider the numbers involved. The star at the center of this system outshines its faint planetary companion by a factor easily running into the tens of thousands. Even the smallest imperfection in the telescope's optics, the faintest stray reflection bouncing off an internal surface, could be enough to bury a signal this weak beneath a wash of unwanted light. Engineers spent years refining the coronagraph specifically to suppress these unwanted reflections to a level that would have seemed almost fantastical only a decade earlier, shaping and polishing internal masks with a precision measured in nanometers, tuning software algorithms to subtract every last trace of scattered starlight without accidentally erasing the very planet they were hoping to reveal. It is a bit like trying to hear a single whispered word spoken from the far side of a stadium packed with screaming fans, and somehow not only hearing it, but identifying exactly who said it. The tool that made it possible was not some entirely new invention built from scratch. It was a coronagraph, a device fitted onto one of the telescope's instruments, engineered specifically to block starlight the way a hand blocks the sun, so you can see a bird flying nearby. This particular coronagraph had been developed with painstaking precision, refined over years, tested and calibrated so that it could suppress the light of a star by a staggering margin, letting only the faintest secondary glow slip through. Without it, TWA-7b would have remained invisible, drowned entirely in the glare of its star, just another shadow nobody could ever prove existed. What is easy to miss in a story like this is just how long the road to this single image actually was. It stretches back years before this particular discovery, to the earliest days after the telescope reached its final orbit and its instruments were still being calibrated. Even then, astronomers were desperate to know whether direct imaging of exoplanets was truly within reach. In one of the telescope's first tests of this capability, it was pointed at a much larger, much hotter, much easier target, a young gas giant several times the mass of Jupiter, still glowing with the heat of its own recent formation, orbiting a star hundreds of light years away. That earlier image was, in its own right, historic. It proved that the telescope's coronagraphs worked. It proved that a machine built primarily to stare at the faint light of the earliest galaxies in the universe could also turn its gaze inward, toward much closer and much colder targets, and pick out a planet glowing softly against the dark. But that earlier planet was, in astronomical terms, an easy catch. Big, hot, young, practically screaming its presence in infrared light. What happened at TWA-7 was something else entirely. It was proof that the technology had matured to the point where astronomers could now find something dramatically smaller, dramatically fainter, hidden inside a messy, glowing disk of debris rather than sitting in open space. It was the difference between spotting an elephant on a plane and spotting a small dog hidden inside a forest. The gap between those two achievements, separated by roughly 3 years, represents an enormous leap in what direct imaging could actually accomplish. Consider for a moment what that means for the decades ahead. Every exoplanet ever discovered through indirect methods exists to us today as a set of numbers, an orbital period, an estimated radius, an inferred mass, a probable temperature. They are, in a sense, more like entries in a spreadsheet than places. Direct imaging turns entries in a spreadsheet into something closer to a photograph, however faint and blurred that photograph might currently be. It turns a statistic into a point of light you can actually point to and say, there, that is a world. Multiply this capability across dozens, then hundreds, then potentially thousands of nearby young star systems over the coming years, and the picture of our galactic neighborhood stops being a collection of inferred data points and starts becoming something closer to an actual map, dotted with real imaged worlds. None of this happened by accident. It is the product of decades of engineering, of a mission that faced its own share of delays, budget battles, and moments where its very existence was uncertain. The telescope now responsible for this discovery spent years in development, survived a launch sequence with hundreds of points of potential failure, unfolded itself in the vacuum of space with a level of mechanical precision that terrified the engineers who designed it, and settled into an orbit far beyond the moon, where no human hand could ever repair it if something went wrong. Every one of those risks was taken specifically so that one day a moment like this could happen. So that a faint point of orange light hiding inside a ring of dust around a star most people have never heard of could finally be seen, confirmed, and added to the very short list of worlds beyond our solar system that humanity has actually looked at directly, rather than simply calculated into existence. It is worth sitting with just how strange this achievement actually is when placed against the scale of the universe itself. 100 light years does not sound like an overwhelming distance when spoken aloud, a small number compared to the vastness of the galaxy beyond it. But translated into physical terms, it means the light captured in that image left its source when human beings on Earth were living through the final years of the 19th century, decades before airplanes, before radio broadcasting, before either World War had begun. That light traveled uninterrupted through the emptiness of space for more than a century, arriving at a mirror built by engineers who had not yet been born when the journey started, only to be caught, sorted, and turned into a single faint orange dot on a screen. Every direct image of a distant world is, in that sense, a message from the past, a fossil of light finally reaching an eye capable of understanding it. There is also a quieter, more human layer to this story that rarely makes it into the headlines. Behind every one of these images sits a team of researchers who spent months, sometimes years, cross-checking their own results before ever submitting them for publication, terrified of announcing a discovery that might later collapse under closer scrutiny. Careers in this field are built and occasionally broken on the reliability of a single claim. That is why the language coming out of the research team has remained carefully measured even amid the excitement, framed in terms of probability rather than absolute certainty, evidence rather than proof. It is a discipline built on distrust of its own excitement, and that caution, however unglamorous, is exactly what gives a discovery like this its credibility once it finally clears every hurdle placed in front of it. Meanwhile, the broader implications of this single image are already rippling outward into the planning rooms of the next generation of telescopes. Instruments currently being designed and built, successors intended to launch in the years ahead, are being engineered from the ground up with direct imaging of smaller, cooler, potentially rocky worlds as an explicit priority rather than an afterthought. The lessons learned from successfully isolating a Saturn-mass planet hidden inside a glowing ring of debris are being fed directly into the design specifications of coronagraphs that do not yet exist, mission concepts that are still lines on an engineer's whiteboard rather than hardware in a clean room. In a very real sense, this single faint point of light is quietly reshaping the blueprints for how humanity searches for the next one. What happens next is, by design, uncertain. Follow-up observations are already underway, refining the planet's mass, tracking its motion, attempting to determine whether its atmosphere carries any detectable chemical signature at all. Other young disk-bearing stars are already being lined up as the next targets for the same coronagraph technique that found TWA-7b, each one a candidate for revealing another hidden world nobody previously suspected was there. Somewhere in that growing list of targets, astronomers privately admit, there's a real possibility of finding something even smaller, even colder, even more startling than what has already been found. Nobody knows which star that will be, or when the data will arrive, or what exactly will be sitting there once the starlight is finally blocked out and the image comes into focus. For now, there is only the quiet certainty that, for the first time, a machine built by human hands looked into the dark around a distant star and did not have to guess. It saw, and this is where the story stops being only about one planet and starts being about a method. Because indirect detection, the technique that gave humanity almost every exoplanet ever cataloged, has a hidden weakness. It tells you a planet is there. It rarely tells you very much about what that planet actually looks like, what its atmosphere contains, whether clouds swirl across its surface, whether storms rage in its skies. Direct imaging changes that equation entirely. Once you can actually see a planet as a distinct point of light separated from its star, you can begin doing something remarkable. You can split that light apart, wavelength by wavelength, and start reading the fingerprint of its atmosphere directly from the glow it gives off. You are no longer guessing at a shadow. You are examining the thing itself. That is precisely why researchers describe this as a threshold moment rather than a single isolated headline. The instruments and techniques refined to catch a planet as faint as TWA-7b are the same instruments and techniques that will eventually be aimed at smaller, cooler, rockier worlds, the kind that might sit in the temperate zones around their stars where liquid water could theoretically exist. Nobody is claiming that has happened yet. The planet captured here is a cold, young, gas-rich world, nothing remotely like Earth, sitting far from any zone where life, as we understand it, could take hold. But the significance is not in what this particular planet is. The significance is in what this discovery proves is now possible. If a telescope can find something this faint, this deeply hidden inside the noise of a debris disk, then the next generation of discoveries suddenly feels a great deal closer than it did just a few years ago. To understand why a single point of orange light could cause this much quiet excitement inside the astronomical community, it helps to step back and remember just how young this entire field actually is. The first confirmed planet orbiting a star other than our own was not found until the early 1990s, and even that discovery came from an unlikely source, a rapidly spinning dead star known as a pulsar, its precise timing signals betraying the presence of small worlds orbiting around it. A few years later came the first planet found around a star, more like our own sun, detected not by seeing it, but by watching that star wobble almost imperceptibly as an unseen companion tugged at it with gravity. From that moment forward, the search accelerated. Entire missions were built for the sole purpose of staring at hundreds of thousands of stars simultaneously, watching for the telltale dimming of a transit, waiting patiently for a planet to pass in front of its star and shave away a fraction of its light. Thousands upon thousands of worlds were cataloged this way, an entire census of the galaxy's planets built almost entirely out of shadows and wobbles rather than sight. Direct imaging, by comparison, has always been the far harder, far rarer path. Only a small handful of exoplanets in the entire history of the field have ever been captured as an actual distinct point of light, separate from their star. Every one of those images required an extraordinary alignment of circumstances. A planet large enough, young enough, hot enough, and far enough from its star to be pulled apart from the star's glare using the technology available at the time. For years, that meant direct imaging was reserved almost exclusively for the biggest, brightest, most obvious worlds, planets so enormous and so freshly formed that they were still radiating away the heat of their own creation like embers cooling in a fire. Anything smaller, older, or closer to its star simply vanished into the overwhelming light of its host, no matter how powerful the telescope pointed at it. This is precisely why the discovery inside the rings of TWA-7 carries so much weight. It did not just add one more name to the short list of directly imaged exoplanets, it rewrote the boundaries of what that list was even allowed to contain. Every planet imaged before it had been a giant among giants, brute force visible simply because of its sheer size and heat. This one was different. This one had to be found using precision rather than brute force, patience rather than luck. A coronagraph engineered with extraordinary care and a data processing technique, refined specifically to tease a whisper of light out of a roaring silence. Astronomers who had spent entire careers assuming that planets this small, this faint, and this deeply buried inside a debris disk were simply beyond the reach of direct imaging were forced to reconsider what the next decade of discovery might actually look like. There is something almost unsettling about how quietly all of this unfolded. No sudden alarm. No emergency broadcast. Just a research team sifting through infrared data, noticing a point of light that refused to disappear no matter how many times they reprocessed the images, refused to be explained away as noise or artifact or coincidence. Science, in its truest form, rarely announces itself with fireworks. It arrives as a stubborn anomaly that will not go away, a signal that survives every attempt to dismiss it, until the only honest conclusion left is that it is real. Skeptics within the field have not been entirely silenced, and this is worth acknowledging honestly rather than glossing over. The odds of a background galaxy contaminating the image were calculated as extremely small, but not zero. Confirmation of a discovery like this typically comes through follow-up observations, additional imaging sessions spread across months or years, tracking whether the point of light moves in a way consistent with orbiting the star, rather than sitting motionless far behind it. That confirmation work continues. Extraordinary claims, especially ones sitting at the very edge of what an instrument is capable of detecting, demand exactly this kind of patient, repeated scrutiny before they are locked into the history books as certain fact. And yet, even with that caution built in, something has already shifted. Before this observation, the assumption among many researchers was that direct imaging would remain limited to large, hot, young gas giants for the foreseeable future, planets so bright in infrared light that they were, relatively speaking, low-hanging fruit. TWA-7b broke that assumption. It demonstrated that with the right combination of a well-placed coronagraph, a sufficiently young and nearby target star, and enough patience in processing the data, astronomers could now reach down into a mass range that had previously seemed out of reach. Each time that ceiling gets pushed a little lower, the range of worlds that could eventually be photographed, studied, and characterized in detail grows a little wider.